Hello, everyone. This week we're going to talk about some of the major concepts and aspects of the TCP/IP protocol. So, networking is going to be super important in terms of some of the concepts you're going to learn throughout the rest of the course when we look at sniffing, when we look at networking, trying to determine various hosts, who they're connecting to, who they're talking to. So, each of the four layers of the protocol stack for TCP/IP are going to be super important. Now we're going to focus on the TCP/IP protocol stack and not the OSI model. Refer back, and I will link back to the Security Plus book by Chiampa for some information on the OSI model, because in most cases people communicate using the OSI model and not the TCP/IP reference model. But this book talks about the TCP/IP reference model, which is fine. Remember, there's four layers to the protocol stack: the application layer, the transport layer, the internet layer, and the network layer. And we're gonna look over IP addressing schemes, how they relate back to TCP/IP, and security. And then we're gonna talk about some numbering systems. Always got to remember your binary, your octal, and your hexadecimal. So remember how to convert numerical bases. Um, so those are the objectives for chapter 2 in the book. So again, what's TCP/IP? You should have a strong background already in some TCP/IP concepts. So again, it's a protocol, it's a language used to communicate from computer to computer. And remember, TCP, unlike UDP, is about resiliency and redundancy. So it's making sure that when a source sends a message to a destination, it gets to a destination. And it is agnostic as to how a message gets sent. So a path could change. Even you could have the same communication. You could send hello from a source to a destination, and it really doesn't matter if it goes through nodes A or B or C or D, as long as the message gets there and it gets there reliably. That's TCP. Unlike UDP, where UDP just blasts the message out, and if it gets there, it gets there. It doesn't care if the message gets there. So UDP is result agnostic, TCP is path agnostic. So TCP/IP is obviously the most widely used. We talked about the four layers already, and I think that's it for this one. I think, oh, here's the layers. So again, you should be familiar with both models from your previous networking courses. But again, your application layer, well, let's start at the bottom. Your network layer, it's the stuff that sends the messages, the physical wires, the physical mediums. And also remember that the network layer of the TCP/IP reference model maps to both the physical and the data link layer of the OSI model. So the network layer within the TCP/IP model is not only your physical but also your first layer devices. Um, so your routers, um, anything that's assigning or using MAC addresses, that is your network layer. The internet layer, that is the layer used to bind the IP address to a MAC address, so your IP address to a physical address, and figure out the destination. The transport layer, that is when we talk about TCP and UDP. That makes sure your packets get to where they're going. With TCP, it matters that it gets to where they're going. UDP, not so much. And the application layer, this is where you translate the packets so that software can understand what you're sending. So when we talk about protocols, HTTP, FTP, that is up at the application layer. Um, all right, so I guess the book wants us to go into the individual layers again. So front end protocols, here's a list of common protocols in the application layer. Again, you should be familiar with all of these, but when you think of any common protocols that you're dealing with, software, FTP, mail, so SMTP, ICMP, um, I'm sorry, ICMP is not in here. I mean IRC. Um, this is the application layer. So typical software-related protocols you're using. Transport layer, again, is really about transporting packets. It's TCP or UDP, making sure that a message reaches your host. If you remember, TCP has a special handshake, SYN, SYNAC, ACK. It's, again, all about reliability, so there is a very specific order to the way TCP handles a handshake. This is where SYN floods come into play, which we'll talk about later. Basically, how to take over all the ports on a host. Because of the way TCP is designed and because of the way computers for the longest time didn't properly handle uh, closing TCP connections that should have been timed out, you would end up with ports experiencing a denial of service attack because of what was called a SYN flood attack. Segment headers. TCP headers, super important to understand. When you go sniff a line and you want to see the communications going over the wire, you need to understand how the headers are broken down. There's a number of flags, there's a sequence number, there's source and destination. You need to understand the way headers are written to look for potential vulnerabilities in the way a program or protocol is communicating. And here is the breakdown of the segment headers. So again, you have your source and your destination, and make sure you also understand that these are fixed sizes up to limits. So dig into the text and also dig into the Security Plus book that accompanies this course to make sure that you're really understanding these header sizes. But again, you have a source and destination. You have your sequence number. So again, if there's 50 packets, what packet is this? What order is it in? Your acknowledgement number. You have offsets and you have your flags. And your flags are also important. Oftentimes you'll hear of attacks relating to some of these flags. So you need to make sure that, with the urgent flag or the reset flag, you're familiar with the various flags. The checksum for integrity of the information and other options. So, dig into the segment headers, the breakdown of what those headers look like and the various sizes. So we talked about flags. These are each 1 bit in size. SYN and ACK for communicating, urgent, what's the priority, the reset flag, finished. Make sure that you understand that the basic order of communications within TCP use these flags to determine what type of message you are sending. So your initial sequence number, it's a 32-bit number that tracks packets that's received by the node and allows it to be reassembled into large packets where it's been broken up into smaller packets. So it's sent in the first 2 steps of the TCP three-way handshake. And remember your three-way handshake. The sending node sends its ISN with the SYN packet, and the receiving node sends it back with the SYN-ACK. So remember that order. TCP ports. So a TCP packet has 2 16-bit fields, and it contains the source and the destination port numbers. And remember, a port is the logical, not the physical component of a TCP connection. So the port identifies the service that's running. So HTTP port 80, some of the older apps 8080 as well. Maybe you'll see a custom port for TCP 443 for HTTPS. Remember your normal ports. So 20 to 21 for FTP, 25 for SMTP, 53 for DNS, 69 for TFTP, 80 for HTTP, like we said. 110 for POP3, 119 for NNTP, 135 for RPC, 135 for RPC, and it's 139 for NetBIOS. IMAP's 143. So remember your common ports. You're not going to want to reference your common ports over and over. So even if you have to make some flashcards, less, I think, for this class and more for just your career, you should be able to see a port, recognize what it is. So your TCP ports, again, the well-known ports are the first, it says 1023. If we're going to count 0 as a port, 1024, because remember, we're working in base 2, so it's all, two to the first, to the second, to the third, to the fourth. So the first 1023 non-zero ports are used. 20 and 21, FTP. FTP is kind of huge for gaping holes at organizations. Oftentimes you'll see FTPs with anonymous access, and when you do your footprinting and when you do your research, FTP and Telnet are some of the items that you should be looking for. But those are examples of some ports connecting to an FTP site. So here's a screenshot. I'm sure at some point you've connected to an FTP site, but this is just an example they wanted to give. We talked about these ports already. I'll just show these slides for a minute so you can see them. All right, UDP. We talked about UDP before. Fast but unreliable. Just because they say unreliable, it's unreliable in the sense that it is agnostic to whether or not the packet actually arrived. The point of TCP is making sure that if a source sends a message to a destination, for as much as it can control it, it gets there. Um, the background of TCP, and we talked about this in the TCP IP course. When we talk about ARPANET, TCP IP was really designed for communication between the government during a nuclear attack. So when you talk about not path traversals, and you don't care, as long as it gets from source to destination, you don't care if it hops through A or B or C through D or B through D. It doesn't matter as long as it gets there. That was the point of TCP. UDP is meant more for large amounts of data where if you miss a packet or two, it doesn't matter. So if you think phone communications, if you think video streaming, if you drop a video frame and you're showing 29.5 video frames a second, is anyone really going to notice? Probably not. And that's where UDP comes in. It just spews data, and if it gets there, it gets there. So it doesn't go through the same amount of redundancy and triple handshake and all the checks that TCP does. So it's not that UDP is unreliable and you shouldn't use it. They're just used for different things. If it really matters, so for instance, if you're sending money, yeah, that matters. If you're trying to do SWIFT 2 over the internet, you want to make sure that your money gets to your account and the proper messages are sent. And it's super important that you should use something like TCP and not UDP for that. The internet layer in TCP. So this layer is used for routing packets to their destination, uses a logical addressing scheme, so in this case IP addressing, and it's connectionless, typical in similar to UDP. The Internet Control Message Protocol, ICMP, probably familiar with it with ping and traceroute. These are network operational messages. So this protocol is used to figure out what's going on in the network, what's TTL, what's happening. So ICMP is used oftentimes for those purposes, and we're going to use that in this course. So these are some typical ICMP codes that you would see if you're doing an echo reply or a or a destination unreachable or redirect. These are some type codes you would get when using ICMP. Good to have a list handy. I don't think you memorize the important ones: unreachable, reply, echo. Um, but this is useful if you're looking at a raw packet to be able to translate this right away. So IP addresses. It's 4 bytes to two major components, and those components can change based on your subnet. So you have 3 classes as well based on the number of the first byte. So class A, class B, class C. Um, so here's some examples. Obviously, class A, what your ranges are, the number of possible networks. You should all be familiar with this from your networking course, your TCP IP course. Um, but you want to make sure you understand the basics of IP addressing and how it breaks down. So when we talk about the addresses and we break them up into their various classes, so you have your 4 octets, um, and class A, the first byte is always reserved for your network address. The last 3 bytes for the host. So again, like I said, the network versus host addresses change based on the class. Class A supports the most host computers because remember, 3 of the octets are dedicated to the hosts. So if you look at the number of bytes available in there, that represents your number of hosts. So that's about 16 million. And then your format, the first octet is the network, and the 3 last octets are your host. B, let's just keep moving down the chain. The 2 first octets are the network address. The last 2 are the hosts. It supports a significantly less number, but again, these are all powers of 2. So this time it's 65,000-ish hosts. And oftentimes these are assigned to ISPs. So you will see Class A's oftentimes assigned to countries or large economic regions. You will see Class B's assigned to your internet service providers. You will see Class C's assigned to companies. And that is next, Class C. These are your three octet network addresses, and it's 254 host computers per address. So again, that's your last octet, your last byte. So subnetting allows an admin to further divide the network into smaller segments. Um, so, when you've heard of and used a subnet mask, that is a representation of a subnet. And you want to make sure that you go back to your previous learnings on subnetting and understand that it's super important for allowing hosts to maintain or hosts in terms, sorry, network admins to maintain control. Every network needs to be assigned a subnet mask, and again, it helps you distinguish the network from the host addresses. So when we look at an IP address in binary, so 128.214.18.16, I don't know why they threw zeros in front of there. I think maybe because they're converting to binary. This would be your binary conversion of that IP address. So your subnet mask if you convert that to binary as well, you have your first three octets, which are all represented as ones in binary, um, and the last is all zeros. So the subnet portion would be the first three octets, and the host portion would be the last octet. So that's just an example of a subnet mask. CIDR notation. So obviously there's various class sizes, but it's the classless interdomain routing notation. So it allows you to essentially efficiently assign IP addresses for a specific space. Long-term, CIDR is not the solution. It's IPv6, which obviously everyone's moving to. Well, some people are moving to. But if you're familiar with CIDR notation, for instance, 192.168.1.0/24 is basically saying that all the hosts, so you have the 254 available hosts under the network address of 192.168.1. So that's CIDR notation. There are the class equivalencies here. So this shows you your various usable hosts and what the CIDR notation means. So for instance, when I said WAC24, 254 hosts, that is representative of essentially what would be a class C. So when I was talking before about 192.168 .0 WAC 24, that would be 254 hosts available with that network portion of that address. So CIDR notation, it's used in a lot of tools that you'll probably use in this course. So make sure that you're aware of kind of the big ones. 24 is often if you're scanning a company, if you're scanning someone's Class C address space, you'll want to know the .0/24 notation because it's often used by the tools themselves. So when you're planning your network segments, if you're building a network, every network segment has to have a unique IP address. You can't, network portion, host portion of an address cannot contain all zeros or ones. Yeah, 0 and 255 are invalid. I don't understand why they just don't tell you are invalid addresses for node points. So you can't set everything to 0 or everything to 1 in terms of the binary equivalencies. Now, that's not to say both of those addresses aren't used. But when you're planning actual segments and you're looking at hosts, you do it by the 254 available addresses that are there. When you access items or hosts on other networks, you need to have a gateway, and that gateway handles communication. The internet layer, again, uses a subnet mask in order to determine the proper destination. So if you have two different addresses, it needs that gateway in order to relay packets properly. And a gateway moves the packet along to the next hop until it eventually reaches its destination. IPv6, the wave of the future is now. Obviously, the number of IPv4 addresses is extremely limited. We hit our cap years ago, and IPv6 didn't include, by default, any sort of tunneling or any sort of encryption. So there's two kind of huge problems with IPv4. Is the address space is super limited now that we have billions and billions and billions of devices. And then the other problem is that it really didn't have security baked in. So what does IPv6 do? It adds those two features. Now it makes IP addressing super tedious but it allows for 128-bit addresses, so you have 2 to 128th available addresses. So pretty much every device you can ever imagine, at least right now, can have a unique address. And also it includes by default a number of security features. So when it comes to IPv6, definitely the way to go. Most businesses probably won't move anytime soon to it. Oftentimes, you'll find home networks and businesses are behind NATs, so network address translation. So you're issued not even a Class C, but one IP address, and then you translate the communication on your network that has its own local set of IP addresses, and its own IP address scheme, which is translated up and ports forwarded at the router level. In terms of natting. So, IPv6 is great if we assume every single device everywhere for all time has a single address, but we know that's not the case. And for the very foreseeable future, probably decades, we're going to have both. All right, so some numbering systems. You need to know your binary, your octal, and your hex. At this point, especially when we start going in packets, you need to be able to do a lot of this in your head. So remember, binary is base 2, octal is base 8, decimal, that you're used to doing math in, is base 10, and hexadecimal is base 16. And remember, hexadecimal is where we have the numbers 0 through 9, and we use the letters A through F to represent numbers 10 through 15, respectively. So the binary number system, 0 or 1, alive or dead. A byte is 8 bits. So a bit is a 0 or 1. A byte is 8 bits. It represents up to 256 different numbers. Remember, when you're writing binary, it is right to left. So the number 0000 0010 would be 2 to the 0th times 0, which would be 0, and then 2 to the 1st, which is 2 times 1, that would be 2. So that would be 2, but you're reading from right to left. File permissions oftentimes are represented by bits. Everything is represented by bits. I don't know why they picked that one out, but sure. Yeah, read, write, execute. Yeah, yes, it's represented by bits. So we're learning the binary number system. This really is memorization of the patterns. So you don't really have a choice. If you want to do this, you got to memorize how the patterns work. That's not even a choice for this class. If you want to convert in your head, you have to know how to do this. So remember, in binary, it's always powers of 2. So what's 2 to the 0th power? 1, 2 to the 1st power 2, 2 to the 2nd power 4, 2 to the 3rd power 8, to the 4th power 16, 5th to 32, 6th to 64, 7th is 128, 8th is 256. You have to remember this. And if you ever are stuck, think of the previous power before it and multiply it by 2, because that's all it is. So if we read binary right to left, there's an example here, starting right to left, 10000010. So what is that? Well, there's 2 ones. There's 2 ones at 2 positions, in the 0th position and the 6th position. So that means 2 to the 0th power times 1 is 2, plus 2 to the 6th power, which is 64, and that gives you the answer of 65. So remember, it's all about the position of where the bits are, and if those bits are turned on, so the value is 1, you multiply, or you add that together with all the other powers of 2 that are also turned on. And that's it. So you just, again, have to remember the position determines the power of 2. and you always start with 0. So the first position is 2 to the 0th power. A nibble is 4 bits. There's a lot of other content on this slide, and all you need to remember is a nibble is 4 bits. That's it. Okay. A low order nibble and a high order nibble. Again, the high order nibble is the left side, the low order nibble is the right. So just think lower numbers, since binary is right to left, lower numbers would be on the right. That's your low order nibble, the first 4 bits. Your high order nibble is the last 4 bits. That's it. Okay. I'm going to skip this because it seems pretty obvious. If you have questions, email me. The octal numbering system is base 8. So if you think about the binary numbering system where it was 2 to the x power, this time it's 8 to the x power. So it's a little easier to understand if you think about it that way. So uses 8 at its base, so supports the values from 0 to 7. So let's start with an easy one. You have a number 5. That's it, 5. So that has a value. So what 8 to the 0th power is 1. 5 times 1 is 5. That's it. Let's say you have an octal number 11. So what is 11 octal in decimal? So let's start with position 0. So you have a 1. A 1 times 8 to the 0th power would be 1. A 1 times 8 to the first power, so 1 times 8 would be 8, so that value would be 9. So 1, 1, that value would be 8, so 1, 1 would be 9. So octal 11 would be 9 in decimal. And that's it. So think about it the same way as you would binary, just the base instead of being 2 would be 8. Hexadecimal, exactly the same way. So instead of your base being 2 or 8 or decimal 10, your base would be 16. So what is the number 5 hexadecimal in decimal? So 5 times 16 to the 0th power would be 5. Your number in decimal would be 5. Let's say you had 11 in hexadecimal. So 1 hexadecimal would equal what in decimal? So 1 times 16th to the 0th power would be 1. Okay, we're good with that. So store that in your head. 1 times 16 to the first power would be 16. So 16 plus 1 would be 17. So 1 hexadecimal would be 17 decimal. And that's it. So again, you treat all this the same way, but the numbering, the bases just change. So remember, binary is base 2, so 2 to the x power. Octal is base 8, so 8 to the x power. Decimal is base 10, 10 to the x power. That's what we're used to using all the time. We add, subtract, multiply, divide, double integral. So that's decimal. And then hexadecimal is just base 16. If you think about it that way, it seems confusing at first, but if you just think that the bases change, clear your mind, it will help you solve these problems a little easier. And you can do all this math in your head. Just take some time to practice. Okay, so the base 64 numbering system. Oftentimes this is used for encoding, and we're not going to do a lot with base 64. Oftentimes base 64 will also be used for obfuscation, but just be clear, base 64 is not encryption. If you encode something in base 64, you're not doing anything except encoding it. That's it. It's an easy conversion. It's almost like a Caesar cipher, where I'm just gonna, add a couple um, positions on my letters and think that I've encrypted it. It might have been good if we were in the Middle Ages, but something like base 64 is not a means of encryption. Oftentimes people will confuse it with encryption, but it's just encoding and obfuscation. That's all. So the base 64 numbering system, again, different characters mapped to different representations. But again, the whole point of base 64 is really just encoding. So, summary, I know this has been a long, another rambling lecture number 2 for you. But again, read your chapter. I always have to hold a reserve. If I mistakenly said something in here, your book is your guidepost here. I am just merely trying to make some of the concepts a little easier. Hopefully, I didn't make them more confusing for you. Um, TCP/IP, again, when we think TCP/IP, think reliability. We want things to work versus UDP, whereas I have a ton of data and I just need to send it off somewhere. The TCP/IP reference model uses 4 layers, unlike the 7 reference model layers of the OSI model. So remember, your application layer is your front end protocols. Your transport layer, this is where data is encapsulated. This is where it could be UDP or TCP, but in this discussion, we focused on TCP. TCP is connection oriented. We want to make sure it's reliable. So it's a 3-way handshake. Um, the critical components of TCP headers, you have your flags, your ISN, source and destination. Um, we need to make sure that we memorize, and this is some rote memorization. I'm not saying memorize the 1023 common ports, but memorize the big ones so that you can easily pick those out of a data dump or of a scan. Remember, your internet layer is all about packet routing, your IP addresses. You have your 4 bytes, your 4 octets, your 3 main classes of addresses, IPv6 wave of the future, but not moving there anytime soon. Uh, and then your numbering systems, and you're just going to have to practice on the numbers. So things you should probably just practice. If I recommend things outside of everything the book talks about, is really get to know conversion between numerical bases. This will help you, so you don't always have to rely on a calculator or Google. And memorize your ports. Um, if I tell you FTP, you should immediately know what that port is. If I say HTTP, you should immediately know that port. If I say 80, you say HTTP. If I say 443, you say HTTPS. You really know the ports, and this is just going to benefit you and speed up the time it takes you to analyze a log file or analyze a network packet that's been captured. And that's it. If you have any questions, shoot me an email. Otherwise, have a great week.